So we're a national user research facility, which means that we award time to do research to anyone that has a good proposal. And as we'll talk about as we walk around, there's all kinds of different science going on. You can call it all material science to put an umbrella over it, but it's everything from studying proteins in your body and drugs to microcircuits to magnetism to solar cells, soil contamination, anything you can think of really. So I'm not the expert on the research that's going on. Maybe we'll see a researcher as we go and can have them give you some details on their experiments. But I know enough to talk about it. What I do know about is the accelerator. So we are an electron particle accelerator. It's called a synchrotron, is the sort of technical name. And the whole purpose is to create X-rays that people then use to do their research. So what we have, if you kind of turn around and look at our cartoon of the facility, we have a storage ring where the electrons, let me just point at it, a storage ring, colorful thing here where the electrons circulate at just about the speed of light, 99.9999995% the speed of light. And as they are circulated around this polygon, it's actually a 36-sided polygon, they're being accelerated in the sense that they're going around corners. Just like you're in your car and you feel yourself pushed to the door, that force comes from acceleration. So they're being accelerated around the corners, and that's usually what we mean when we talk about a particle accelerator. There's other accelerations going on to get them up to speed, but as they go around the corners, they basically are, they're given extra energy. And the way that they shed that extra energy, if you want to think about it that way, is that they emit radiation. And this is a fundamental principle of physics. Any charged particle, when accelerated, will emit radiation. We tune the machine to operate at that speed I was talking about, or 1.9 billion electron volts is the other way we say it, to produce radiation in the form of mostly X-rays or ultraviolet light. It actually produces a rather broad band of spectrum, everywhere from, we actually do produce visible light, all the way through ultraviolet, extreme ultraviolet, soft X-ray, and hard X-ray light, which, as you guys know, is just one part of the electromagnetic spectrum, right? We're looking at each other with another part of the electromagnetic spectrum, the visible part. And we actually produce visible light, we produce infrared. Some people use infrared to do experiments as well. So the electrons are accelerating around in the vacuum chamber, and as they go, they're shining off X-rays. You can kind of get a visual picture. Think of a toy locomotive on a little track going around a circle with a headlight, and the headlight is kind of sweeping around as the thing goes around. Every time it sweeps across one of these beam lines, which are the straight lines, a flash of X-rays goes down the beam line and hits the sample that people are trying to study. And I say flash of X-rays, most of the beam lines can't actually discern these flashes of X-rays because the electrons are going the speed of light. But there are some beam lines that can see the flashes of X-rays, and we'll talk about one as we walk around. So we have about 300 bunches of electrons, and I'll tell you a little bit more about why they're bunches when we're actually in there kind of looking at parts of the accelerator. And as they go, they're flashing X-rays down the beam lines, and we have about 40 X-ray microscopes, basically, at the end of all of these beam lines, doing all kinds of things. You can see here, this is a measure of the number of electrons we have. 500 milliamps, half an amp. So it turns out that that's some hundreds of billions of electrons all bunched in the accelerator. One thing I'll say is that the beam of electrons is extremely small. You'll see that this is a very large facility, but we make a very small beam. The beam is about the same size as if you took 2 hairs off your head and put them side by side. So it's about 30 microns, depends on where you are in the ring, but it's about 30 microns, 30 millionths of a meter high by about 100 microns wide, something like that. And what you gain from having such a fine beam is that all the photons, or radiation, that's coming off of that beam, they look like they're coming from an extremely small spot. And so in one of the beam lines, you can take all that really powerful light and refocus it into a really small spot. As you can imagine, when you're looking at very fine structures, or even atomic bonding, things like that, you want as small a probe as possible, because you probably know the resolution criteria, the Rayleigh criteria. You need a wavelength twice or half the size of something you want to look at. So it's useful to have a small beam with all the photons coming in a very small spot. We make a lot of photons. So if you do a comparison to the surface of the sun, if you were to go to the surface of the sun and take the same size spot and compare it to coming out of some of our devices in the storage ring, we would be billions and billions of times brighter or more powerful than that surface of the sun. So that's really the power and the utility. That's a collider, right? And in that accelerator, it's very similar. Pretty much the same technology. We all use the same math. But they have two beams counter-propagating. And then in certain points, 4 different points in the machine, they focus those beams down as tightly as possible and collide them together. That's where the collisions happen and where they study the fundamental particle physics. I joke that if we're colliding, we're doing it wrong. We need to retune the machine so the electrons fly around. And the electrons don't last forever. They bounce off of each other. They're all negatively charged, so they repel each other. They also bounce off residual gas molecules that we have inside the ring. And that brings up the fact that we operate under extremely good vacuum conditions. So inside the storage ring and most of the beamlines, the vacuum is about the same quality as on the surface of the moon. We say 10 to the minus 10 or 10 to the minus 11 torr. And that's necessary just so there aren't particles of gas, carbon monoxide, ionized atoms flying around for the electrons to hit and get lost. And so